Dopamine gets you addicted. Serotonin is the happiness molecule. Oxytocin is the love hormone, and you're unhappy simply because your brain is chemically imbalanced. These slogans are popular and satisfying, but most of them are oversimplified, and some are just plain wrong. This isn't to say chemistry doesn't matter. Quite the opposite. Neurotransmitters and hormones really do profoundly shape how you think, how you feel, what you want, and how you decide and act. They are real levers. These chemical imbalance stories actually have a historical origin. In the 1950s, doctors stumbled onto something. A blood pressure drug pushed some patients into depression, while a tuberculosis drug lifted people's mood, and both, as it happened, affected the monoamine transmitters. The monoamine hypothesis was born, later simplified into chemical imbalance, and then carried to the public by marketing. It's a compelling story, but as you'll see, the truth is far more complex than that slogan. Here's the key. These levers act on specific processes: wanting, learning, sensitivity to punishment, alertness, inhibition, not on vague feelings like pleasure, happiness, or love, and certainly not on character. Mapping a molecule one-to-one onto a feeling is wrong from the very start. So this episode is a mechanism first, honest tour. What these chemicals actually do in the brain and body, how solid the evidence is, and which claims are overblown. I'll flag it all along the way. What's been repeatedly confirmed, what's only moderate or preliminary, and what's popular but doesn't hold up. To keep you from being fooled, I'll grade the evidence in 3 tiers. Repeatedly confirmed, like the reward mechanism of addiction or the cholinergic damage in Alzheimer's. Partial or moderate, like many links between hormones and mood. And popular but shaky or already overturned, like serotonin equals happiness. Learning to sort each claim into these 3 tiers is what this episode is really trying to teach you. Let me put the single most important sentence right here. No chemical maps onto one feeling or one personality. Behavior is the output of a whole interacting network. Ready? Let's start with how a signal travels. Your brain has roughly 86 billion neurons. When a neuron's electrical signal reaches its tip, it releases a chemical, a neurotransmitter, that drifts across an ultra-thin gap called a synapse and lands on a receptor on the next neuron, passing the signal along. Then it's cleared away by reuptake or breakdown. This is the physical basis of every thought and emotion in your brain. Here's a crucial point that's often missed. The effect of the same molecule depends entirely on which receptor it lands on. Dopamine has D1, D2, and other receptors. Serotonin has more than a dozen. One molecule can excite you in one place and calm you in another. So, more dopamine equals more pleasure doesn't even make sense mechanistically. We should also distinguish 3 modes of action. A neurotransmitter is a fast, point-to-point, millisecond signal inside the synapse. A neuromodulator spreads out diffusely, tuning the gain of a whole circuit on a slower timescale. And a hormone enters the bloodstream, travels the whole body, and acts for minutes to hours. Interestingly, molecules like oxytocin and norepinephrine can act as both a transmitter and a hormone. Almost every psychiatric drug plays with this machinery. In SSRI, a selective serotonin reuptake inhibitor doesn't add serotonin to your brain. It blocks the reuptake step, letting serotonin linger a little longer in the gap. Stimulants increase the release of dopamine and norepinephrine, and many drugs activate or block one specific receptor. Hold on to this release-receive reuptake logic, and the rest will all hang together. Once you get this, you can see through an expensive misconception. Get your blood serotonin level tested. That's almost meaningless, because the blood-brain barrier blocks the way, because the brain's signaling is local and instantaneous, and because about 90% of your body's serotonin is made in the gut and never reaches the brain. The number in your peripheral blood often has nothing to do with what's actually happening in your head. The conclusion is firm. To this day, no commercial neurotransmitter test can diagnose your mental state from blood, saliva, or urine. When you see a product saying, "We measured your low dopamine, so buy this," you can swipe it away. Holding this mechanism ruler, let's pause on a more basic question that science explainers usually skip. How do we actually know any of this? Before we go on, it's worth seriously asking, how were these conclusions about brain chemistry actually reached? Because the limits of the methods directly determine how trustworthy the evidence is. And that's the key to telling a hard conclusion from an exaggeration. In a living human brain, neurotransmitters are extremely hard to measure directly. One of the most common tools is positron emission tomography, PET, which uses a radioactive tracer to estimate the availability of a certain receptor or transporter. It's powerful, but ultimately just an indirect snapshot. Magnetic resonance spectroscopy gives an indirect estimate of glutamate and GABA in a brain region. Cerebrospinal fluid is closer to the brain than blood, but still imperfect. And there are pharmacological challenges, like tryptophan depletion, temporarily lowering serotonin's raw material to see how behavior changes. Each method captures only one slice of the truth, and the precise tools that can truly establish causation, like optogenetics and chemogenetics, switching specific neurons on and off with light or chemicals, can mostly only be used in animals. This creates a core tension. In animals, you can prove causation, but can't cleanly generalize to humans. In humans, you can observe, but usually only get correlation. Remember this one thing, and you'll have a kind of immunity. When you hear chemical X causes behavior Y, silently ask 3 questions. Is this evidence from humans or animals? Is it causal or correlational? Was it directly measured or inferred from peripheral blood? Those 3 questions filter out most exaggeration. Good. With that ruler in hand, let's meet the first and most misunderstood character, dopamine. The popular story is, dopamine equals pleasure, equals reward. Scrolling your phone, eating something sweet, getting a like, a hit of dopamine. It sounds right, but it goes wrong at the most important step. What dopamine actually encodes is the reward prediction error and incentive salience, that is, wanting. It tags a goal with, "This is worth pursuing," and drives you to chase it, to put in effort, to learn what action gets what. It governs wanting, not liking. This prediction error isn't speculation. It was recorded directly in a classic experiment. The neuroscientist Wolfram Schultz gave monkeys a cue, then a squirt of juice, while recording dopamine neurons. At first, dopamine fired when the juice arrived. But once the monkey learned that the cue predicts juice, that burst moved earlier, to the moment of the cue. And if the cue came but the juice didn't, dopamine actually dipped at the expected moment. What it reports is better or worse than expected, not pleasure itself. That feeling of pleasure, of liking, is generated mainly by opioids and endocannabinoids in the brain's hedonic hotspots. Wanting and liking are 2 different systems. And that explains the cruelest part of addiction. The more addicted someone is, the more frantically they often want, while liking it less and less. It also explains why phones and slot machines are so sticky. What drives wanting hardest isn't a steady reward, but an uncertain, intermittent one, a variable ratio. Will the next video be funny? Is this message for me? It's exactly this suspense that keeps the dopamine system nudging you to scroll once more. Not because you're weak-willed, but because this system was built for uncertain rewards in the first place. The hardest evidence comes from a 2025 meta-analysis in JAMA Psychiatry pooling 107 randomized controlled trials, giving people dopaminergic drugs only enhanced reward learning and reward vigor, with almost no effect on processing punishment. If dopamine equals pleasure were true, the results shouldn't look like this. That is strong evidence. Dopamine has 4 main pathways. The mesolimbic pathway handles motivation and reward learning. The mesocortical pathway handles working memory and cognitive control. The nigrostriatal pathway handles movement and habit, and the tuberoinfundibular pathway suppresses prolactin. Worth noting, dopamine in the prefrontal cortex follows an inverted U, too little or too much, both impair your cognitive control. When it goes wrong, the death of dopamine neurons in the substantia nigra causes the movement problems of Parkinson's. Elevated presynaptic dopamine synthesis and release in the striatum is linked to the positive symptoms of schizophrenia, one of the most replicable findings in all of psychiatry. Abnormal dopamine and norepinephrine signaling is linked to ADHD, which is why stimulants work. And the dopamine flood produced by addictive drugs is essentially a hijacking of this reward learning system. One more detail helps you grasp dopamine's many faces. It has two firing modes: a slow, tonic background firing that sets your overall motivation level, and fast, phasic bursts that mark the moment something is better than expected. This also explains why Parkinson's patients beyond slowed movement often have apathy too. The loss of dopamine takes the very drive to want to do things along with it. And let's bust an internet buzzword. Dopamine fasting or dopamine detox has no neuroscientific basis. You can't and don't need to empty out dopamine. It was never a stockpile of pleasure, but a signal that drives you to act. Serotonin equals the happiness molecule is probably one of the most deeply rooted claims of all. But that same 2025 meta-analysis also showed manipulating serotonin in people affects punishment learning and the processing of aversion, with almost no effect on reward. It is not a happiness switch. Serotonin is more like a broad-spectrum regulator and buffer. It modulates mood, helps you wait more patiently for delayed rewards, processes punishment and threat, restrains impulses, and is involved in sleep, appetite, and sexual function. The RAFI nuclei spray it diffusely across the whole brain and with more than a dozen different receptors. That's why its effects are so varied. What about depression? This was the biggest argument of the past few years. An influential 2022 Umbrella review concluded, there's no consistent evidence to support the simple model that low serotonin causes depression. Overnight, the serotonin hypothesis has been overturned, spread across the internet. But here you have to be careful not to overcorrect. The more balanced view points out, serotonin is still part of a multifactorial model. And there's a more crucial distinction. Whether antidepressants work and whether you're actually deficient in serotonin are two separate questions. A 2018 study pooling 21 antidepressants found they all beat placebo, with a moderate average effect. A drug being useful does not prove a chemical imbalance exists. There's an important clue hidden here too. An SSRI raises serotonin in the synapse within hours. Yet its antidepressant effect usually takes 2 to 4 weeks to appear. That delay strongly suggests that what actually works isn't topping up serotonin itself, but the slow downstream neuroplasticity changes it triggers. Once again, don't reduce a complex downstream adaptation to supplementing a substance. By the way, serotonin's 5-HT2A receptor is the site where psychedelics like psilocybin and LSD act, and it's now one of the hottest frontiers in depression research. Psilocybin therapy has received the FDA's Breakthrough Therapy designation and entered late-stage clinical trials. But to be honest, it is still investigational and away from routine approval. Here's a yardstick for how small the effect is. A meta-analysis linking serotonin to aggression pooled 175 samples in over 6,000 people and found serotonin explains only about 1% of the variation in aggression. So claims like low serotonin makes people violent or the MAOA warrior gene determines crime are badly overstated. Look at one specific disorder, OCD. Its first-line drug is a high-dose SSRI, higher than what's needed for depression, which itself hints the mechanism is different. The current picture is an overactive corticostriatothalamic circuit involving both serotonin and glutamate. And beyond drugs, a behavioral therapy called exposure and response prevention is just as crucial. Once again, it's a circuit, not a single molecule. Dopamine and serotonin are the stars, but the two truly most abundant transmitters in your brain are actually two others: glutamate, the main excitatory transmitter, and GABA, the main inhibitory one. The balance between them, the ratio of excitation to inhibition, is the core dial that stabilizes cognition, mood, and sleep. Through receptors like NMDA, glutamate handles fast excitatory signaling and synaptic plasticity, the physical basis of learning and memory. But once it runs out of control, it causes excitotoxicity, a mechanism of damage and stroke, traumatic brain injury, and neurodegenerative disease. What does learning look like physically? When two neurons fire repeatedly and almost simultaneously, the connection between them via NMDA receptors gets strengthened. This is called long-term potentiation, the cornerstone of memory at the synapse. There's a neat old saying, neurons that fire together, wire together. Behind everything you've ever learned, glutamate is reshaping these connections. A discovery that rewrote depression treatment. Ketamine, an NMDA receptor blocker, can relieve depression within hours. This pulled the whole field's attention away from monoamines and toward glutamate and synaptic plasticity. Its clinical effect is strong evidence. The exact mechanism behind it is still moderate. GABA, meanwhile, quiets neurons down. Benzodiazepine tranquilizers, alcohol, and the brain's own neurosteroids all act on the GABA-A receptor, producing anti-anxiety, sedative, sleep-promoting, and anti-seizure effects. The new drug for postpartum depression works precisely through this neurosteroid, GABA pathway. This excitation-inhibition ratio lens is reshaping how we understand some disorders. In autism, one hypothesis is that excitation is relatively too strong, which may relate to the sensory overload some people experience. And in schizophrenia, dysfunction of inhibitory cells called parvalbumin interneurons is thought to disrupt the cortex's rhythms. To be clear, these are still active research frontiers, not settled conclusions, but the thinking is far deeper than missing some transmitter. So, a more accurate view is many psychiatric symptoms are less about too much or too little of a transmitter, and more about the balance of excitation and inhibition being thrown off within specific circuits. This view is far more accurate than one substance, one disease. Next, a few modulators. Norepinephrine comes from a small nucleus in the brainstem called the locus coeruleus and projects to nearly the entire brain. It tunes alertness, attention, and adaptive gain, roughly whether you focus on the task in front of you or explore widely. It surges under stress and helps carve emotionally intense events firmly into memory. Some non-stimulant ADHD drugs act on this very system. The relationship between your norepinephrine level and your performance is an inverted U curve. Too low, and you're drowsy and can't grasp the point. Just right, and you're alert and focused. Too high, like in extreme anxiety or panic, and attention actually collapses, becoming narrow and chaotic. That's why moderate stress boosts performance while excessive stress destroys it. Acetylcholine governs attention, the encoding of memory, and cortical arousal, and flags novelty and uncertainty. In early Alzheimer's, it's precisely the cholinergic neurons in the basal forebrain that degenerate, which is where cholinesterase inhibitor drugs come from, with gentle, symptomatic effects. In September 2024, a brand new class of antipsychotic, Cobenfy, was approved, acting on muscarinic acetylcholine receptors, no longer relying on blocking dopamine. It's the first antipsychotic in decades that doesn't take the old dopamine road. One more word along the dementia line. Cholinesterase inhibitors are mostly symptomatic. They ease symptoms without changing the disease course. But in the last few years, Alzheimer's treatment finally reached the threshold of modifying the course. Anti-amyloid antibodies like lecanemab and donanemab can clear plaques from the brain and slow cognitive decline by roughly a quarter to a third. But be clear-eyed, this is slowing, not a cure. And it comes with risks like brain swelling and microbleeds that need close monitoring. It's a real advance, and also a magnet for overblown expectations. The acetylcholine line carries one very practical warning. Many common drugs, certain allergy meds, sleep aids, even some antidepressants, have anticholinergic effects. In older people, the accumulation of these drugs can impair memory and even trigger delirium. This is a badly underrated yet often reversible, cognitive risk. Here, knowing the mechanism is directly a matter of medication safety. Histamine isn't just for allergies. Histamine in the hypothalamus keeps you awake, which is exactly why many antihistamine drugs make you drowsy. Notice the pattern that keeps recurring. Every transmitter isn't a single function, but is tuning a whole set of processes. Picture them as different sections of an orchestra, not individual on-off switches. That's the key to understanding the whole system. Orexin, also called hypocretin, is a small group of neurons in the hypothalamus that stabilizes wakefulness, integrating sleep, arousal, energy, reward, and stress. If these neurons are lost, you get narcolepsy. One of the clearest examples in neuroscience of losing a transmitter directly causing a behavioral change. A new class of insomnia drugs is based on this very system. Melatonin is the timing signal the pineal gland secretes in darkness, helping align your body clock and initiate sleep. Let's correct a misconception. It's not a powerful sleeping pill. It's more of a "it's nighttime now" time signal. And there's a molecule you deal with every day: adenosine. Every waking moment, your brain steadily accumulates adenosine, which builds an ever stronger sleep pressure and makes you drowsy. What caffeine does is actually simple. It impersonates adenosine and occupies its receptors, so the brain doesn't receive the signal that it's time to sleep. So caffeine doesn't really give you energy. It just temporarily masks your sleepiness, and once it's metabolized, the backed-up sleepiness comes back all at once. Let me also make clear why sleep matters so much for mood. Sleep isn't shutting down, but an active, staged process. Deep sleep restores the body and consolidates memory, while REM sleep is like unloading the baggage from your emotions. After one sleepless night, the amygdala's response to negative stimuli is significantly amplified, while the prefrontal brake weakens. That's why, when sleep-deprived, you're more irritable, more impulsive, and more likely to see small things as big. Sleep and almost every mental state are bidirectional. There's also a cautionary case worth telling: substance P. It's very active in pain and stress circuits, and was once full of promise. Drugs blocking it were thought to treat depression and anxiety. But in larger clinical trials, those drugs failed, and its final home turned out to be a very good anti-nausea drug. Another reminder: a molecule being involved in an emotional circuit does not mean targeting it will cure the illness. Endocannabinoids are the brain's dimmer switch. Made by neurons on demand, they tune synapses backward and finally, managing recovery after stress, the extinction of fear, appetite, and the pleasure of liking. And let's bust a popular claim. The so-called runner's high more likely comes from endocannabinoids than from endorphins, because beta-endorphin actually struggles to cross the blood-brain barrier. Endogenous opioids, including endorphins, handle pain relief, generate the pleasure of liking, and buffer the warmth of social contact and the pain of separation. This is the heart of the brain opioid theory of social attachment. And there's neuropeptide Y, a signal of stress resilience. Studies find that under extreme stress, people with a stronger neuropeptide Y response are less likely to be broken. It's a promising, but not yet druggable, resilience target. Now we switch from the fast signals inside the brain to the slow ones that travel the whole body: hormones. They enter the bloodstream and act over a wider range and a longer time. But one iron rule first: a hormone number in the blood does not equal an effect in the brain. Receptor density and sensitivity, binding proteins in the blood, pulsatile and circadian secretion, the brain's own neurosteroids, and conversion in tissue, like testosterone, turning into estradiol in the brain, all make the same blood level produce completely different brain effects. Cortisol and its HPA axis are the command center of stress. The hypothalamus, pituitary, and adrenal glands pass the signal down step by step, finally secreting cortisol with a strong circadian rhythm. Under acute stress, it mobilizes energy, sharpens attention, and carves emotional memories deeper. But chronic overload makes the hippocampus and prefrontal cortex fragile and the amygdala more sensitive, the so-called allostatic load. Cortisol has a clear rhythm: Shortly after you wake, there's a sharp cortisol awakening response that rouses you and launches your day. Then it gradually falls through the day. Two rare diseases like natural experiments show its power. Cushing's disease, with too much cortisol, brings mood swings and even psychiatric symptoms, while Addison's disease, with too little, brings deep fatigue and apathy. Here's a counterintuitive point. In post-traumatic stress disorder, baseline cortisol is often low, along with stronger negative feedback. Once again, this shows the simple narrative, the higher the stress hormone, the worse, doesn't hold. Stress has an even more far-reaching dimension: timing. Early life adversity, chronic neglect, abuse can, through mechanisms like epigenetics, leave durable marks on the HPA axis and these circuits, raising a person's stress baseline for life. But remember that earlier line. Neuroplasticity means these marks, though durable, are also partly reversible, which is precisely the hope behind every intervention. Thyroid hormone is a great imposter of mood. An underactive thyroid looks a lot like depression, fatigue, sluggishness, low mood, brain fog, while an overactive one looks a lot like anxiety or mania, restlessness, palpitations, irritability. That's exactly why a proper workup for a mood problem always checks the thyroid first. Now, the metabolic hormones. Insulin doesn't just handle blood sugar. In the brain, it also affects eating, reward, and cognition. Leptin reports energy stores are sufficient and suppresses appetite. Ghrelin is the hunger signal, also tied to food reward and stress eating. So yes, hunger really does change your mood and your decisions. This link is real. Here's the hottest current example, which happens to tie metabolism and reward together. GLP-1 drugs like semaglutide, the weight loss shots everyone talks about. They started as diabetes drugs, but turned out to act directly on the brain's reward center, lowering dopamine's reward signal, quieting the food noise that won't leave many people's heads. And more interestingly, they're now being trialed for treating addiction, once again showing that metabolism, reward, and addiction are all wired into the same network. And there's the immune system. Inflammatory cytokines like IL-6 and TNF trigger a kind of sickness behavior, fatigue, anhedonia, social withdrawal that overlaps heavily with depression. But mind the nuance. Anti-inflammatory treatment only helps the subset of depressed patients with elevated baseline inflammation. It's not a general antidepressant. Inflammation also has a hidden pathway to mood. When the immune system is activated, it diverts tryptophan, the raw material for making serotonin, down another route called the kynurenine pathway, both reducing serotonin supply and producing metabolites that affect neurons. This is a concrete mechanism for how inflammation lowers mood, not just a vague correlation. See, all these systems, once again, connect to each other. Since we're on the gut, we have to mention the gut-brain axis. The microbes in your gut can affect the raw materials for neurotransmitters, signal upward through the vagus nerve, and modulate the immune system's inflammatory tone. It's a mechanistically tantalizing direction. But honestly, in humans, it's mostly still at correlation and preliminary, and a long way from the claim that eating something can fix your mood. Sex hormones profoundly modulate the brain and are tightly tied to the stages of life. Estrogen is neuroprotective and pro-plasticity and modulates serotonin, dopamine, and acetylcholine, which explains why the premenstrual phase, the postpartum period, and perimenopause become windows of mood vulnerability for some people. Here's an important clarification. Premenstrual dysphoric disorder, or PMDD, is not abnormal hormone levels, but a brain that is unusually sensitive to the normal hormonal swing. Likewise, postpartum depression is not simply the hormones dropped. There's another often overlooked window: puberty. The surge of sex hormones happens to coincide with the remodeling of the brain, especially the prefrontal control system. That's why the risk of many mental health problems rises sharply around puberty. The sex difference in depression and anxiety also begins to show from this time. Hormones here aren't an isolated cause, but one strand interwoven with development and social pressure. A metabolite of progesterone, called allopregnanolone, is a potent modulator of the GABA-A receptor, and it's precisely this neurosteroid pathway that produced the new postpartum depression drug mentioned earlier, a success driven directly by mechanism. Testosterone affects libido, spatial cognition, and responses to status and competition, but its effects are context-dependent and usually small. More than raw aggression, it seems to tune status competition, which is called the challenge hypothesis. And let's bust a widely circulated claim. Testosterone does not impair men's cognitive empathy. Two large randomized controlled trials in 2019, with 643 men total, 15 to 25 times larger than the small study that once reported a positive result, found no such impairing effect. On estrogen and cognition, there's another often misreported point. Taking estrogen protects the brain and prevents dementia. That claim is actually contested. Timing and formulation matter, and there may be a critical window. But at present, hormone therapy is not recommended for cognition as a routine measure. Once again, the truth is more complex than the headline. The pattern is the same. Sex hormones are powerful modulators, but what they tune is tendency and sensitivity, strongly swayed by life stage, by context, by psychological framing. Never one hormone, one behavior. One last deified star, oxytocin, often called the love hormone or the trust molecule. But the truth is far more complex. What oxytocin modulates is social salience. It makes social cues more prominent and important. But its effects are highly context and person-dependent. It can boost your trust and closeness toward your own people while also boosting your defensiveness and bias toward outsiders. It is not a substance that indiscriminately makes people kind. Intranasal oxytocin boosts trust. That widely circulated conclusion under rigorous scrutiny turned out to rest on weak, inconsistent evidence with publication bias problems. And oxytocin in peripheral blood or saliva doesn't reflect central brain activity well at all. A sobering lesson comes from autism. It was full of promise, but the large-scale trials of oxytocin and of vasopressin-related drugs largely all failed. It reminds us that social neuroscience findings that are fascinating in animals often can't be cleanly carried over to the human clinic. On pair bonding, there's a story told countless times. Prairie-voles bond for life, while their close relative, the montane vole, does not. And the difference lies in the distribution of oxytocin and vasopressin receptors in the brain. The finding is so fascinating that it got applied straight to humans. But that's exactly the lesson. Voles are not people, and cleanly transplanting animal social neuroscience onto human love and trust has failed again and again. Vasopressin, oxytocin's close relative, is involved in social recognition, pair bonding, territory and aggression, and tuning the stress axis, and often shows clear sex differences. But likewise, the human evidence for it is far more cautious than the animal evidence. By this point, the most important lesson is really this. Pulling each molecule out to look at it alone is exactly the mistake we're most prone to. Behavior is what emerges from a whole interacting network. A few recurring interactions are worth remembering. Dopamine and serotonin keep each other in check, one tilting toward reward and activation, the other toward punishment and inhibition. Glutamate and GABA maintain the excitation-inhibition balance. And the HPA axis, monoamines, plasticity, and inflammation are tightly coupled. Chronic stress can cause glucocorticoid resistance, pushing the body into a pro-inflammatory state, one of the leading models linking stress and depression. And there's more. Sex hormones modulate the monoamines, creating life-stage windows of mood. Sleep and the circadian rhythm affect mood bidirectionally. Sleep loss amplifies negative emotion and weakens self-control. And between gut, brain, immune system, and endocrine system, there's a mechanistically rich axis too. Though in humans, the causation is still mostly preliminary. This leads to a key conclusion. Psychiatric disorders are more like a dysregulation of this network than missing or having too much of a single molecule. A genetic study spanning 8 disorders and 160,000 cases showed that genes related to dopamine and serotonin are shared across diagnoses, and don't produce the clean one disease, one signature mapping. Precisely because genetic risk is shared across diagnoses and symptoms overlap, the research community has begun trying a new approach. Rather than fixating on diagnostic labels, study dimensions that cut across disorders like reward, threat, cognitive control. The idea behind this is exactly what this episode keeps emphasizing. The brain is organized by processes and circuits, not by the diagnostic names we invented. And one more yardstick that must be said honestly. The effect of a single chemical on real behavior is usually small. In meta-analyses, mostly a standardized effect size of 0, 2 to 0, 3, and personality traits often explain only a few % of the variance. Those big headlines of one molecule makes you X are almost all built on inflated, actually tiny effects. With this network lens, let's look back at a few common psychiatric disorders, and we'll find none of them is missing one molecule. Each is a dysregulation of a whole network. Depression is the best example. What's most supported now is the joint involvement of glutamate plasticity, stress biology, inflammation, and dopamine's reward dysfunction. The serotonin explanation is still clinically useful, but far too weak as a single cause. Depression is very likely not one disease, but a syndrome with several different biological subtypes. In schizophrenia, dopamine is still central. Elevated presynaptic dopamine in the striatum is one of the most replicable findings. But the modern picture also adds glutamate NMDA hypofunction, problems with GABA interneurons, neurodevelopment, and the immune system. A neat way to put it, dopamine is more like the final common pathway of psychosis, not necessarily the original source. ADHD is one of psychiatry's clearest success stories. At its core is a signaling problem of dopamine and norepinephrine in the frontostriatal circuit, which is why stimulants and atomoxetine work. It's highly heritable and is not caused by eating sugar nor simply by poor parenting. Anxiety and PTSD, meanwhile, involve an excitation, inhibition imbalance, norepinephrine overarousal, the HPA axis, and the learning and extinction of fear in the amygdala, prefrontal circuit. Notice what they share. For almost every disorder, the most accurate description is multifactorial at the network level, not too much or too little of some chemical. If we had to pick one case that ties all the previous systems together, it would be addiction. It enlists nearly every character we've discussed. Act 1 is dopamine. Addictive drugs produce a dopamine flood far beyond any natural reward, hijacking reward learning. The brain is taught over and over. This is extremely important, worth chasing at any cost. And so, wanting is pathologically amplified. But as we said, wanting and liking split apart. With tolerance, the same dose brings less and less pleasure, while wanting grows ever stronger. This is the cruelest part of addiction, no longer enjoying it, yet unable to stop. Act 2 is glutamate. It welds cues and reward tightly together. A place, a smell, a group of people can all become a trigger for craving. It's exactly this glutamate-based learning that explains why, long after quitting, a single cue can still cause relapse. Act 3 is the dark side. After long-term use, the stress systems, CRH, dynorphin, are pushed into overload, bringing anxiety, irritability, and deep discomfort during withdrawal. At this stage, many people keep using not for the high, but only to escape the pain of withdrawal. Putting the 3 acts together, the mainstream model has a crisp summary. Addiction is a disorder of reward deficit and stress-surfeit, which is also why it's understood as a brain disease, a dysregulation of the reward, motivation, and self-control circuits. But please note, this absolutely does not mean blame biology for everything. Genetics, development, trauma, and the social environment are equally powerful shapers. Understanding the neurobiology is precisely so we can help more effectively and more compassionately, not so we can pass the verdict weak-willed. After all these processes, you might ask, what about personality? Can it map onto some chemical too? It's a tempting question, but one to handle with great care. Some influential frameworks have tried. Cloninger's theory of temperament, for instance, loosely links novelty seeking to dopamine, harm avoidance to serotonin, and reward dependence to norepinephrine. It sounds tidy and appealing, but modern evidence tells us these links are dimensional, correlational, and small in effect. Personality traits are about 30 to 60% heritable, which precisely means the environment accounts for a big half too. And personality is highly plastic, continually reshaped by learning, relationships, and experience. No temperament is written in stone by any single molecule. So the more accurate way to put it is, neurochemistry shapes the starting tendency of your emotions and behavior. What more easily ignites you? What's harder for you to restrain? But a starting tendency is not a destination. And that, precisely, is the shared foundation of both responsibility and the possibility of change. Having seen this network clearly, let's spend the last few minutes honestly on an often misused question. Since so much of this is chemistry and hormones, does that mean my brain decides me? The answer is, biology shapes tendencies, not destiny. High heritability does not mean unchangeable. It's a statistic about variation across a population. It shifts with environment, and it says nothing at all about whether you can change. Genes only act through environments. Some people are even more sensitive to both good and bad environments. And neuroplasticity lasts a lifetime. Learning, relationships, and psychotherapy genuinely reshape your synapses and circuits. There's also an often overlooked direction: reverse causation. Exercise, stress, sleep, and diet all change these chemical systems in turn. So an abnormality you measure may well be a consequence or a compensation rather than a cause. Mistaking correlation for cause is the most common error in this field, and precisely for that reason, the levers that can move these systems go far beyond drugs: psychotherapy, regular sleep, exercise, whose antidepressant and anti-anxiety effects are actually quite robust, plus social connection and nutrition. They act on the same biology drugs do. Medication is an important tool, but it often needs to be used together with these. Take exercise. Why does it work? Exercise raises a brain-derived neurotrophic factor called BDNF. You can picture it as fertilizer for neurons, promoting the growth of new connections and supporting plasticity. That's why non-drug levers like exercise, sleep, and therapy can genuinely change this system at the biological level, and not just as psychological comfort. So what this episode really wants to leave you with is this: these molecules are real levers, but they act on processes, not on feelings or personality. Understanding them adds compassion, treatability, and the possibility of change, not a label of being born defective. Next time you see a headline saying some molecule turns you into something, I hope you'll take out today's mechanism ruler and weigh it for yourself. Is this repeatedly confirmed? Is it overstated? Or is it just plain wrong?